Hey, everybody. Hey. Yeah, not much. How about you guys? Yeah. Whenever yeah, you guys are always so busy nowadays with just so much going on. I know seniors, I know you guys have senior design too, so that must be really tiring. I don't know. Oh, I mean, it's our second day of lecture for this class, so in that sense, it's kind of like a Thursday, but Thursday for us. But yeah, it's only the middle of the week. Yep, Monday is a holiday, so we're not going to meet on Monday. All right. Any good animes to watch? Well, let's talk about that later. All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
Just was it recording or is it recording?
Yeah, it's recording.
Okay.
Yep. So it's Wednesday. So week 3. So you know we're really getting into the semester, right? Okay. So first thing I want to announce is that Monday is a holiday. Oh, yeah, Monday's a holiday, so we're going to take a day off on Monday. So in honor of our presidents, so it's President's Day, and so we're not going to have lecture. So after today's lecture, the next time we meet is going to be next Wednesday. Okay. But I will have office hours on Monday. So if you want to come by and you had questions on the homework or anything, you know, I'll be there from 9 to 10 on Mondays. And if you want to set up an appointment to talk about something at any other point during the day, I'm open to that too. But we're not going to have lecture, and you know we'll take the day off from that. Okay. Okay. So today, you know, we're going to spend a good amount of today in MATLAB actually, and so you know we spent all of last class applying the finite difference scheme to a diffusion equation. Now we're actually going to see how that's actually implemented in MATLAB. Okay, and so while I'm kind of talking right here, if you can open up MATLAB, that would be great. I also have posted a starter code on Canvas as well. And so if you go into the course outline and you click on the link for week 3, you should see at the bottom there that there's a I think it's the second bullet point under files for the starter code for today's activity. Okay. There's not really much in there, so it's excuse me. So there's basically just some commented lines, but it'll at least help you guide. Excuse me. Sorry. It'll at least help guide us through our activity today. Okay. Okay. And so another announcement I want to make is that I graded your homeworks. So your grades, you should see your grades for those on Canvas. And so remember, for this class, since it's an elective class, I like to grade my homeworks for these based on just completion. So I didn't really leave any feedback for you guys. And so, once, usually after I grade the homeworks, I post the solutions. So, definitely go in and check the solutions and just to make sure that you have things right there. Okay. All right. So are there any questions I can answer before we get started? Okay. All right. So I'm going to do a little bit here on the iPad just to kind of refresh our memory from Monday. And then from there, I'm going to hop onto my laptop and go into MATLAB. Okay. So again, remember, if you want to follow along in today's lecture, definitely have MATLAB open, download the starter code, and then that would be kind of a good starting point. Okay. Okay. And so just a refresher from where we were before. And so if you remember from last time, we started to apply our finite difference scheme to our equation. Okay. And so we started with kind of the simplest equation that we can do under these circumstances, which is the 1D diffusion equation. Okay. Okay. And so the general form for this equation is it's given by the following. Oh, the starter code is under week 3. So if you go to the Canvas site and click on the link for week 3, it should be there under files. Yeah. Mm-hmm. Yeah. So the general form for our diffusion equation is the following, right? And so we had gamma, and then we had a second order derivative. So we had d squared theta, or d squared phi dx squared is equal to sum q of x, right? So this is the general form. So last time we worked with kind of a specific example, but this time, just for generality, I'm going to show you kind of the general form of this. Right? Oh, we're going to use the second one. So we're going to use the file that's titled 1D Diffusion Class Activity MATLAB Starter Code. Yeah. It's the second one that's on there. So it's 1D Diffusion Class Activity MATLAB Starter Code. Yeah. Mm-hmm. Okay. And so from this equation here, we have this lambda right here, or this gamma, I guess. This is our diffusion coefficient. Okay. And then on the right here, we have our source function. Okay. Right. Yeah, so it should just have comments. Yeah. Mm-hmm. Yeah, so there's not much in there, but the comments will kind of help us guide the code. Yeah. Okay. And so what we did last time was we applied finite differences. Because remember, what we have up top here is this is a differential equation. And so in order to solve this in MATLAB, we need to convert this into a set of algebraic equations. Right? And so to do that, we need to take the derivative and turn it into a finite difference approximation. Right? Okay. And so after we apply finite differences, we get this almost like a recurrence relationship between the phi values at different grid points. Okay. And remember, the i's in this equation right here, they represent the different nodal ID numbers in our grid, right? And so let's say that we apply this onto a grid of 6 points. Okay. And so if we do that, then we can start plugging in, we can start deriving equations for each of the different nodes here, right? And so let's say that we start at I is equal to 2, right? And so if we apply this at I is equal to 2, what we get is gamma over delta x squared times phi at I plus 1. And so since I is 2, we have phi 3, okay, minus 2 phi at I. So we have 2 phi 2 plus phi at I minus 1. So we have phi 1, okay, is equal to qi. Okay. Generally, what we like to do is we like to move all the coefficients over to the right-hand side, okay? And so we're going to take this term out in front here and then move it over to the right. Okay. Okay. Right. And so from that, we're able to derive an algebraic equation for this finite difference scheme, okay? And then what we can do from here is we can apply this at all the different nodes in the mesh, right? And so we've applied it so far on node 2, but then we can do the same things for node 3, node 4, and node 5, right? And so we can basically apply this this finite difference equation to all of our interior nodes, the ones that aren't on the boundaries. And then for the boundary nodes, if you remember, what we did was we applied boundary conditions. Okay.
Professor.
Yep. Mm-hmm.
Sorry to interrupt. Are we going to be finding a solution or plotting?
We're going to be doing both, and so we're going to find the solution first, and then we're going to plot it. Yep.
Okay.
Mm-hmm. Okay. And so let's say, just for the sake of argument, or just for this case here, we have a Dirichlet boundary condition on the left-hand side. Okay. And so for the Dirichlet boundary condition, remember we're directly specifying the solution value there. And on the right-hand side, let's say that we have a Neumann boundary condition. Okay. And so let's say that our Neumann boundary condition is d phi 6 dx is equal to gamma. Okay. And then once we apply basically all of these guys, we're going to have a system of linear equations. And so in this case, since we had 6 grid points, we're going to have 6. Our system's going to be 6 by 6. Okay. Right. And then, you know, if we extract the coefficients from our equations, we get the following pattern, right? Okay. All right. And so it's the return of problem 3C. Okay. And on the right-hand side right here, we have our Dirichlet boundary condition and our Neumann boundary condition times delta x. Okay. And then for all of these guys, we have, you know, the forcing function multiplied by the by delta x squared over gamma. Okay. Oh, it's 2, 3, 4. Okay. So this is kind of the more general form of that matrix system. So I think last time we applied it to a specific problem, but you know, as you kind of generalize for different values of the diffusion coefficient and different values of the function and different boundary conditions, this is kind of what you get right here. Okay. And so before we dive into the code, I did want to show you guys the general form of this, you know, before we actually start to solve it. Okay. All right. And so, you know, when we write our MATLAB code, basically we're gonna need to do you know, several different tasks. And so the first thing we need to do is, you know, define this left-hand side matrix. Okay. And so we're gonna find out, we're gonna, you know, implement a way to implement the coefficients here, right? Then we're going to implement a way to define this right-hand side forcing vector. Okay. And then from there, we're going to solve, and then we're going to plot and analyze the solution. Okay. All right. But for this activity that we're going to do, we're actually going to solve, you know, the equation that we were working on last time. And so just to kind of remind you, this was our equation. Okay, so we d squared phi dx squared is equal to 6x, right? And then we have the following boundary condition. So we have our Dirichlet boundary condition on the left-hand side, right? And so we said on the left-hand side, our solution has to equal 1. And on the right-hand side, right, where x is equal to 1, we're going to have our derivative here equal to 0, okay? And so if you kind of relate this to kind of this general form right here, right, you should see that our diffusion coefficient is equal to 1, okay? And our q of x is equal to 6x, okay? All right, so this is specifically the problem that we're going to solve on in our MATLAB code, okay? Okay, and we're going to do, and for the MATLAB code we're going to do it for a grid of 6 different 6 points, okay? So basically this exact same problem right here, okay? Okay, any questions on this before we dive into the MATLAB code? Okay, all right, so let me go ahead and share my screen. Right, and so if you have the MATLAB starter code open, you should have this, okay? Right, so does everyone have the starter code up? Okay. Okay, and so let's go ahead and walk our way through, you know, what goes into each of these different sections here. Okay. All right, so the first step, you know, that we're going to do is we're going to define our variables, right? And so if you remember from our MATLAB review, you know, variables are going to be useful things for us to store some important variables, okay? Or store important quantities that we're going to use later on, okay? And so we're going to need a couple of different things here. So first thing we're going to need is we're going to need a variable to store all of the x coordinates for all the nodes, okay? Right? Because each of the different nodes in our grid, so if I can can kind of pull up these nodes at the same time, right? And so if you look at this grid right here, here I've started from 0, but we can start from 0 or 1. Each of these grid points is going to have a different x coordinate, right? And so node number 0 here is going to have an x coordinate of 0. Node number 1 here, or node number 5, I should say, has an x coordinate of 1. And then everything else here should be evenly spaced. So node number 1 should have an x coordinate of 0.2. Node number 2 should have 0.4, 0.6, 0.8. So basically things are evenly spaced, okay? And so luckily for us, we have a function in MATLAB that will allow us to create such a vector. Right? And so if we first, let's create a variable called pos vector, okay? And we're going to use the MATLAB function called linspace, right? And so if you remember, linspace creates a vector for us that lets us, define the starting point, the ending point, and the number of points in between, right? Okay. And so our starting point here is we need to have a starting x value of 0. Okay. Our ending x value needs to be 1 because that's where we want to end up with on the right-hand side. Okay. And then from here, we have to define the number of points that we want to have in our grid. Okay. And so in this case, we want 6 points, right? Because we have a 6-point grid. Right? Okay. So then if you run this code, so right now it's not really doing anything interesting, but we can at least run it and see what happens, right? And you can see this pos vector is filled now with the x coordinates of each of the nodes, right? And so you can see node number 1 has an x coordinate of 0. Node number 2 has an x coordinate of 0.2. Next one is an x coordinate of 0.4, 0.6, 0.8, and then 1, okay? And so we basically effectively created, a variable that will store all the coordinates between 0 and 1, okay, for our 6 grid points. Okay. Any questions on this so far? Okay. All right. And so now that we have our position vector, next thing that we need to do is we need to define the grid spacing. Okay. Okay. And so if you remember from our equations up here, you can see that a big part of our equations is going to be delta x squared. But remember, delta x here is the spacing in between the grid points, okay? And so let's define another variable called dx. Okay? And then we're going to set this to be the spacing in between each of these grid points, okay? And so in this simple case, we can just simply, hard code it in. And so since we know that between each grid point is going to be 0.2, we can just, set it to 0.2 just like that, okay? But later on, what I'll show you is, how you can actually write this code to be more general, okay? But we'll get there. Okay, and so that's, the grid spacing. So now we have a variable for that. Now let's create a variable to store our, left-hand side matrix and right-hand side vectors, okay? Because if you go back to our, our system here that we want to approximate, we need basically a vector or a matrix right here to store in all of these coefficients here. And we also need a vector here to store in all of these guys. And so for now, we can just kind of create just empty containers for those guys. And then we can go ahead and fill those in later, okay? Okay. So let's start with the left-hand side matrix. And so since, we want to, usually what we want to do is we want to start with an empty matrix. So we can start with our zeros function, and then we're going to specify this. Now we're going to specify the size of this matrix, okay? And so since this matrix is going to be a 6 by 6, we're going to do 0, 6, 6, okay? And so if you go ahead and run this code and you check left-hand side matrix, right? You'll see that we now have an empty 6 by 6 matrix where all the entries are 0, okay? And so as we write the code, we're going to fill in the entries, the correct entries for this matrix, but for now, we're just going to leave it empty, okay? And similarly, we can do write a similar line of code for the right-hand side vector, okay? Again, we're going to start with an empty vector and then fill it in later, right? And so for our right-hand side vector, we're going to use the command zeros, 6, 1. And so that'll create a vector that's 6 rows and then 1 column. Okay? And then again, we're going to fill those fill those guys in later. Okay. All right, any questions on this so far? Okay. All right, so far so good. So far we've just defined variables, okay? Now we need to fill in the left-hand side matrix, which is kind of this next section of the code, okay? All right. And so in this case, since we have six nodes, we know exactly what our left-hand side matrix is going to look like. And so let's go ahead and start modifying entries in left-hand side matrix, okay, such that our left-hand side matrix will match what we have on the left right there. Okay. All right. And so typically I like to do this row by row, okay? And remember, you know, it's any entry with a 0 in there, we don't need to do anything with it because it's already starting at 0. And so we only need to assign the non-zero entries. Okay, and so let's start it with the first row. So in the first row, we only have one entry there that is non-zero, okay? And that's in the 1, 1 slot. So it's in the first row in the first column, right? And so the way that we can do this in code is we can do left-hand side matrix at 1, 1, okay, is equal to 1, okay? All right, so pretty simple. Okay. And then the rest of the entries in the first row are going to be 0. So we're just going to leave those. We're just not going to do anything about those, okay? All right, so now let's start going to the second row. Okay. Right, so once again, I'm going to call left-hand side matrix. And this time I'm going to reference the coordinates 2, 1. And so that's second row, first column. Okay. And from our calculations, we see that this has to equal to 1. Okay. Right, so next is going to be the one immediately to the right. And so that's going to be left-hand side matrix 2, 2. And from our matrix there, we can see it has to be -2. Okay. And then finally, for the last entry in this row, it's going to be in coordinates 2, 3. And the value for this has to be 1. Okay. Okay. And so I'm going to go ahead and you know, probably some of you guys have already moved ahead anyway. And so let's go ahead and fill in the rest of the entries into the matrix. Okay. And so now I'm going to go to the third row. And so this is going to be 3, 2, 1. Okay. Okay. So that's the entire third row. You can see this is a little bit tedious because, you know, we're doing this entry by entry. But after this, you know, I'll show you how you can do this with a loop, right? Which you've already done. So you've already kind of done problem 3C on the homework. So all of that will just be kind of applying 3C to here, okay? But we're going to throw a little bit of a wrinkle into it too, where, you know, we'll do it for an arbitrary amount of nodes, okay? But we'll cross that bridge when we get there. So let's go ahead and finish typing up these entries. Okay. And so that's the third row. So let's do the fourth row now. Question. Right. So the question is, wouldn't it be easier just to write out the 6 by 6 matrix if we know the coefficients? That's true. Yeah. So in this case, you know, a 6 by 6 matrix isn't that big, and so you can just write it out directly into one line if you want. But the reason I'm doing it like this is because this kind of more closely mimics, you know, what you would do if this were like a 50 by 50 system, right? Because if it's 50 by 50, you're not going to go in and do that manually, and you wouldn't do it like this either. But you know, doing a 50 by 50 system with the loop, it kind of more closely resembles this more so than, you know, typing, you know, kind of hard coding the matrix in directly. Yeah. Okay. And then we finally have our last row. And so be careful with the last row, because the last row, remember, we it's different because of the Neumann boundary condition. Okay. Okay. And so let's go ahead and run the code just to make sure that we have the right matrix. Okay. And so, everyone kind of photocopy this into their memories. And then if we check the actual matrix here in the MATLAB console, you can see that we have the right entries. Okay. So we have 1 and all zeros in the first row. Then we have our pattern of 1, -2, 1. And then on the last row, we have -1 and 1. Okay. Right. Was everyone able to do this part here? Yeah. So Tyler, all we did was we just filled in the entries to this matrix. Yeah. So Juan, so for this one that's okay, but then after this we'll see how we can how we can extend this for like a grid of 50 parts. Okay. Which is fittingly is going to be one of the first problems on your next homework assignment. Okay. But we'll get there a bit later. Okay. And so now that we have our left-hand side matrix here, and so then now we need to fill in the right-hand side vector. A question: does MATLAB allow you to append a matrix to a matrix? I think you can append a row to a matrix. I think you can append a row, but I don't know if you can append. I don't know if you can append columns or like another or like that. But if you want to put like another matrix on the bottom of another one, I think MATLAB can do that. But I don't think it can do columns all that well. Yeah. Okay. And so now we need to write out the values of our right-hand side forcing vector. Okay. Okay. And so for that, I'm going to come down here, and this is the actual code for this particular problem, right? Because the one I was showing up here, this is for the general case for for generic q, but in this case our q is of the function 6x. So I think it'd be more useful to have this one here. Okay. All right. Because right now our right-hand side vector is empty. Okay. And so what we need to do now is fill in those values with what they actually need to be. Okay. And so the first entry is simple. So our first entry of the right-hand side vector is just going to be 1. Okay. Because that's going to be our Dirichlet boundary condition. And so that's what we got when we applied that guy. Okay. All right. And so now let's do the second row. Okay. And so you can see from the from our hand calculations here that the value that we want to put in here is 6 times x1, which x1 is the coordinate for this first node right here, okay, times delta x squared, right? All right, so let's do x1 first. So x1 here, that's the x coordinate of that first interior node, okay? And so if you remember from when we first started this MATLAB activity, like 10 minutes ago, we created this variable up here called pos vector, right? And so what this pos vector allowed us to store was the basically the x coordinate for all the nodes in our grid, okay? And so we can reference that here in this vector, right? And so if we do 6 times pos vector at 2, okay, and so that'll be the x coordinate of the second node, okay, which is exactly what we want right here, okay. And then to that we can just multiply by dx squared, which is dx by dx, okay. And so let me write a comment here. So recall, pos vector contains the x coordinates for all nodes in the grid. Okay. All right. Any questions on that? Sure. Mm-hmm. Mm-hmm. Right. So pos vector. So the question is, what is pos vector of 2 pulling out? And so you're right that pos vector at 2, that's referencing an entry in a vector, right? And so right. Yeah. So that's so any function. So this pos vector of 2 right here will basically give us x. And so pos vector at 2 gives the value of x at the second node in the mesh. Okay. And so since we just need x right here, that's why we just do pos vector at 2. Right. So that's the x coordinate of that node. Yeah. Yeah. And so if our forcing function was like 6x squared, then we would multiply by another pos vector at 2. Right. Right. Because each time we call pos vector at 2, that's referencing the x coordinate for that node. Okay. And so, depending on what our forcing function looks like, you might have to do different combinations of pos vector. Yeah. All right. Okay. And so let's go ahead and fill in the rest of the entries here because they all look very similar. Right? And so we're going to do right-hand side vector at 3. It's going to be 6 times pos vector at 3. Okay. Times dx. Notice this time I use pos vector 3 because we want the x coordinate for the next node, for the third node, instead of the second one. Okay.
Professor?
Yep. What's up?
So the first number in this the right hand side is 1.
Yep.
And the last one is 0, right?
Correct. Yep. Mm-hmm.
And each of those in between is just being multiplied times 6 times dx.
Right.
All times dx squared, I think.
Yeah, delta x squared times x.
Wouldn't it be easier to do like a for loop and then just, like I was saying earlier, just append or change the, like you can do for I or k of 1 through 4 and then just do for starting at your element 2 and then multiplying onwards and just updating the things, the array.
Yep. No, you're exactly right. So actually the traditional way to do this and what we're going to do next is we're going to do sections 2 and 3, but with a for loop. Because, writing out like lines of code like this, you can copy and paste too, but it's inefficient because, right now it's okay because we're doing 6, but if we change this to 50, that's a lot of copying and pasting that you have to do. So, we're going to do that part with the loop, but I want to do it next. I want to do this first just because this one's a little bit more explicit, and then because from here and then going to the loop, I think that's a little bit of a less of a jump of logic than like this. Yeah, but you're absolutely right. Normally you would do this with the loop. All right, question. So you can't just do caret 2. Yeah, you can do that too, and so you can just do just like this as well. Yeah, but I like it. But if it's just squared, I usually just like to type it out like that. But if you want to do, raised to the second power, that's fine too. Okay. Okay. Any other questions on this so far? Okay. And so now that we've defined the left-hand side matrix and the right-hand side vector, now all we need to do is solve our system. Okay. And luckily, this part is really simple because once you define the matrices, MATLAB has a special function to solve these systems for you. Okay. Okay. So I'm going to define a new variable called FD solution. So FD solution stands for finite difference solution. Okay. And all this is going to be our left-hand side matrix backslash our right-hand side vector. Okay. Right, and that's all you have to do. And then once you do that, MATLAB will go ahead and solve your system. Okay, so let's go ahead and run our code, and then we can see our solution. Okay, and here's what it looks like. Right, so actually solving the linear system is probably the easiest part of these codes because MATLAB kind of does all that for you, and that's where we're leveraging computers. Okay, and so if you kind of look at this code and kind of stand back a bit, basically all we've done is we've basically set up the problem for MATLAB here. And so, we've defined the matrices and we defined the vectors. And then from there, the part that's really annoying and really tedious to do, which is solving a linear system, we let MATLAB kind of handle that for us. Okay. Right. So that's our finite difference solution. Okay. And so, for all intents and purposes, we're done here. So, this is the solution right here. But, viewing the solution like this as just like a vector of numbers is really inconvenient. Yes, I'll be posting this code afterwards. Yeah. Yeah. And so what will be more useful is if we visually viewed this code, right? Or visually viewed this solution, because right now seeing this, it's okay, but it'd be nice to just plot this guy. Okay, and so we're going to plot our solution here. Okay? And luckily, we have everything we need to plot the solution already. All right, so first thing we need to do when we plot is we need to define a figure. And so we're going to do figure 1. Okay. Then we're going to plot our finite difference solution. Okay. All right, so remember, when you use the plot function, you need to first define what's going to be your x-axis. And so our x-axis in this case is going to be pos vector, okay? And then our y-axis is going to be, our finite difference solution, which is just what we just computed here, okay? All right, and so before we run this, just, as a good habit, let's go ahead and give our plot a name, okay? So this will be FD solution to diffusion. Okay. Let's go ahead and label our x-axis. So our x-axis is just going to be x. And our y label is going to be solution. Okay, so let's go ahead and run the code. Okay. And here is our solution. Okay. And so it's a little bit jaggedy, because we only have 6 grid points, but this solution here is our finite difference solution. All right, so was everyone able to obtain this solution here? Okay, what was your error? Oh. Yeah, I think MATLAB doesn't like spaces in its file name, and I think it doesn't like it to start with a number. Oh, okay. Yeah, go ahead and check your solution against, go ahead and check your code against what's on the screen right now, because this is correct right here. Oh yeah, you have to be very careful with the spelling. So MATLAB is very particular with the spelling. Yes, capitalization matters, and so if you call this one FD capital S solution, then you can't do lower S solution here, because that'll give you an error. Yeah, error. Okay. Right. So the question is, how do we smooth out the graph? Yeah, that's a great question. So that's what we're going to do in a little bit. Right. So actually, the way we're going to smooth this graph is we're actually going to increase the number of grid points, right? And so if you kind of look at this graph, you can see that there's six grid points, right? And so there's a grid point at each one of 0.2. And so the way that we can actually smooth this out is to increase the amount of grid points, right? Because 6 is really small. So 6 is, if you're going to do a finite difference solution with 6, it's kind of not worth it, because you don't really get that great of a solution. But after this, we'll see if how we can actually extend this to, let's do 50. And then once we do 50, you can see then the grid points will be much closer together, and then we'll converge onto our exact solution. Yeah. Okay. So, but before we do that, let's actually plot the exact solution so that we can compare. Okay. Because remember, for this problem, we actually found an exact solution to the problem. Okay. All right. So normally, for a lot of problems, especially in 2D, you're not going to be able to do this, because 2D problems, it's really hard to solve by hand. But for 1D problems, we can find these solutions, and they're usually not that big a deal. So let's go ahead and take advantage of that. So I'm going to define a new variable called solution exact, and I'm going to hard code in our solution. So this is the solution that we found kind of at the beginning of class last time. Okay. And so if you remember from class last time, our exact solution was x cubed minus 3x plus 1, right? And so the way that we implement that in code is we do pos vector, because remember, pos vector is our kind of manifestation of x, okay? Dot raised cubed. Remember, we use the dot here to do element by element operation instead of, taking that vector and doing vector-vector multiplication, which is what we don't want, okay? And then we do minus 3 times pos vector. So this is minus 3x. And then we do plus 1. Okay. And so that's all we get to do for that. Okay. And so what I'm going to do is I'm going to plot this onto the same graph. Okay. Okay. And then after this, let me hold off. All right. So let's go ahead and run our code. And in red right here, you can see our exact solution. Okay. And so you can see they're different, right? So kind of at the left-hand side here, we're pretty close, but on the right-hand side of this domain, we're pretty far off. Okay. And the reason we're far off is because, again, we've only used 6 grid points. Okay? And so if we want to get a more accurate solution, we need to increase the amount of grid points. Okay. Okay. All right, and so that's what we're going to do next. And so we're going to move on from 6 grid points, and then I'll show you how to write the code for that. Okay. All right. Any questions on this so far? Okay. All right. So let's go about writing the code to make this more accurate. Okay. And so if you looked at the next homework 2, this is actually going to be the subject of 2A. So this is actually part of your homework. Okay. And so I'm going to go ahead and modify this code such that we can do this for an arbitrary amount of grid points. Okay. Okay. And so the first thing I'm going to do is I'm going to specify a new variable. And what this variable is going to do is it's going to specify the number of grid points that we want. Okay. Okay. And so I'm going to call this variable n, big N. And so that's kind of the standard that we'll use in this class, is we'll use big N to denote the number of grid points. Okay. Okay. So let's say that we want to do a solution here with, let's do 50. Let's do 50 grid points. Okay. All right. And so now that we're doing a solution with 50 grid points, we need to modify our grid, right? Because right now our pos vector is finding, the grid points, is finding 6 different grid points between 0 and 1, right? And so we don't want 6 anymore. So now we want to change this to 50, which is what we have, right? And so we can do 50 here. And so this is fine. And so that'll work. But, if we wanted to go back and change this again later, we'd have to change this in 2 places. So let's save ourselves some work. And instead of using 50, let's use big N right here, okay? Because big N is already a variable that stores how many grid points that we want. And so we might as well just use that guy, to define our grid, okay? All right. Okay. And so that's our pos vector. And so now we need to modify our grid spacing, okay? And because our grid spacing is no longer 0.2. Okay? And so actually, this grid spacing now is going to be much smaller than that. So there's a few different ways that we can compute this grid spacing. Okay? One simple way that you can do this is you can just do pos vector at 2 minus pos vector at 1. Okay. And so what this will do is it'll take the difference between the x coordinate of the second grid point minus the x coordinate of the first grid point. Okay. And since all of our grid points are going to be equally spaced, this will give us the grid spacing for everywhere in the grid. Okay. And so that's one way that we can do it. Or we can just simply divide by the number of spaces in our domain, okay? And so the total length of our domain is 1. And so one thing we can do is we can just do 1 divided by n minus 1, where n minus 1, that's the number of spaces that we have in our domain. Right? Okay. We use minus 1 here because, you know, we have 50 grid points, but we only have 49 spaces in between the grid points, right? And so we do 1 divided by n minus 1, and that'll tell us how big each of those spaces are. Okay, and so you can do either one. So both of these will work. So actually, I'm going to use this one right here. All right, any questions on this so far? Okay. All right, so next thing we need to modify is our left-hand side matrix and our right-hand side vector, okay? Because instead of a 6 by 6, now we have a 50 by 50 system, right? Because we have 50 grid points, okay? But once again, instead of writing our 50 right here, we might as well use this n variable since we already went through the trouble of defining it, right? And so let's say that our left-hand side matrix is going to be n by n, and our right-hand side vector is going to be n by 1, okay? Okay. Okay. And so now we've defined our variables and we've modified them to be kind of more general, so that now we can do this for a grid of 50. Okay. And so the next step here is we need to specify our left-hand side matrix. And so we can't do this anymore because, you know, if we did this for 50 a 50 by 50 matrix, you know, our code would just be kind of way too long. And so I'm going to go ahead and comment this out for now. Okay. And then let's write code that will help us do this kind of much more efficiently, right? And so if you remember from our homework 1, the legendary problem 3C, you know, that code right here is going to be really helpful because ultimately what we want is we want to have a matrix that has the following pattern, right? And so, you know, we're going to do something different on the first row and the last row, but for all of the interior rows, we're going to have this pattern. We're going to have a -2 on the diagonal, a 1 on the off diagonals, okay? And so why don't we just write a loop to kind of do this for us, okay? Okay, so I'm going to write for row index is equal to 1 colon n, okay? Because we want to repeat this loop n times, okay? Right. And then from here, let's go ahead and write our if statements, okay? All right, and so let's do the case for the first row. And so if row index equal to 1, okay, then what we need to do is we need to set just the diagonal entry. Okay, and so the way that we reference that is going to be left-hand side matrix row index, comma row index. Okay, and then according to our Dirichlet boundary condition, we know that this guy has to equal to 1. Okay. All right, so that's the condition for the first row. Now let's write the condition for the last row, right? And so in order to reference the last row, we have to do else if row index equal to n, okay? Okay. And then we need to set 2 entries here. So the first entry that we need to set is the diagonal entry, okay? And so that's going to be equal to 1. And then the other guy we need to set is the one immediately to the left of the diagonal entry, right? And so the way that we're going to reference that is row left-hand side matrix at row index, comma row index -1. Okay, and this is going to be equal to -1 because that's the entry that we want to put into that space right there. Okay. Right. And then so now we've taken care of the first row and the last row. And so now let's go ahead and write the code for all the interior rows, okay? And so in the interior rows, in all the interior rows, we need to do two specifications here, okay? Or three, sorry. Okay. Okay. And so with that, we've go ahead and specified our left-hand side matrix. Okay. All right. And you can see here, so for under the else statement, so this is for all the interior rows, we've set the diagonal entry equal to -2. We've set the left neighbor equal to 1, and we've also set the right neighbor equal to 1 as well. Okay. So we can go ahead and delete this guy. Right. And there is our left-hand side matrix. So is everyone caught up here with the code? WPM, I have no idea. Funnily though, like when I was in elementary school, like we took those, and like our computer teacher made us play this game called Mavis Beacon Teaches Typing, which I don't even know exists anymore. But like I was actually pretty terrible at that when I was growing up. So I don't think I type very fast now, especially compared to a lot of my friends. Maybe if we have some free time at the end of the semester, we can do that. But we have a lot we need to cover. Yeah. Okay. All right. So there's our left-hand side matrix. Now we need to write the code to define our right-hand side vector. Okay. And so just like we did for the left-hand side matrix, we're going to do this with the loop. Okay. Okay. All right, so we're going to write the loop we're going to start the loop in the same way because we need to visit every single row of this right-hand side vector. Okay. And just like we did before, we're going to have three different conditions. Right? All right, so first we have a condition for the first row, and we know for the first row, we're going to set it equal to 1, okay? Right, because that's what we have up here, basically, okay? All right, and so our next condition we're going to do is the last row, which I guess technically we don't have to do it because it's already 0, but let's just be complete about it, okay? And so this can be else if row index is equal to n, okay? And so we're going to have right-hand side vector at row index is equal to 0. Okay. All right. Okay. And so the last thing that we need to do is all the interior nodes, right? And so we're going to follow this exact same format that we did up here, but instead of hard coding in the indices here, we're going to use row index. Okay. And so we're going to have right-hand side vector at row index is equal to 6 times pos vector at row index times dx times dx. Okay. Okay. And so this will take care of our right-hand side vector for us. Okay. Okay. Any questions on this? Okay. All right. And so now that we've defined our left-hand side matrix and our right-hand side vector, we can go ahead and run the code again. Okay. And you can see here our graph is a lot smoother, right? It's a lot smoother and it's a lot closer to the exact solution, right? And so the reason it's a lot smoother, remember, is because now we have 50 grid points. And so now, there's a lot less space in between the nodes. And so that produces a much smoother and much more accurate graph. Okay. And the best thing about this now is that, now that we've written this code like this, we can actually have it be more general, right? And so let's say that, we want to do a solution with 500 grid points now, okay? Right? And so since we've written this code to be general with these for loops here, MATLAB will automatically already kind of adjust all these matrices for you. And as you can see with 500 grid points, the two graphs are basically on top of each other, and we get a very, very accurate solution. Right, so was everyone able to get a solution like this? Yeah, so this is basically the answer to 2A. Yeah, so the reason I'm doing this in the class is that last year when I assigned this, I had the class kind of try to figure out these for loops by themselves, and it was tough, because I think it's one thing to kind of say that we know how to use for loops and if statements. But to actually put it in practice, I thought I'd demonstrate it first. Just to give you guys, just so that we can start from a good place. Because from here on out, especially once we start doing 2D problems, it's going to get a lot more difficult from here. Yeah. So I thought I'd show you, kind of my logic and kind of walk you through how to do a problem like this with for loops, so that in the future, once we do this kind of for everything, then we'll have already kind of walked through one together. Yeah. All right. Yeah, it's a lot of code. Yeah, but here you go. So this is basically our first code right here, right? So this is our first solution here. And so you can use this code right here, and you can kind of adjust it to solve different equations. Right? And so this is as someone already noted, this is basically the solution for 2A. But you can actually use this code to help you with 2B as well, right? And so 2B is not exactly the same as this, of course. And so you're going to have a different forcing function and different boundary conditions. But you can use the same framework to kind of handle that as well. Okay. Okay. All right. So now that we've kind of done a code together, now let's talk about one more thing before we sign off for the week. And so if you look in the lecture notes, you can see that there's another section here on using other finite difference schemes, okay? And so let's go over this kind of pretty quickly here. And so if you kind of remember from our derivation, what we used, the finite difference scheme that we used for our second derivative looked like this, right? And so we had phi I minus 1 minus 2 phi I plus phi I plus 1, okay? Divided by delta x squared. And so that using this finite difference scheme produced this stencil. So another word for this kind of matrix here is called stencil. Right? And so this is about as simple of a stencil as you can get, because this is the simplest finite difference scheme that you can use for the second order derivative. Right? And if you remember when we talked about Taylor series, we said that this scheme right here was second order accurate, right? And so in other words, the leading error term was delta x squared. Okay. But this isn't the only finite difference scheme that you can use for a second order derivative, right? And so actually, another one that you can use that's more accurate, it looks like this, okay? And so instead of this simple one, you can start to bring in I plus 2s and I minus 2s, right? So another finite difference approximation for this is minus phi I minus 2 plus 16 phi I minus 1 minus 30 phi I plus 16 phi I plus 1 minus phi I plus 2, okay? All divided by 12 delta x squared, right? And so this is obviously a lot more complicated, and it's going to be a lot more work, but your work will be rewarded because you end up with a scheme that's fourth order accurate here, okay? And so that's a lot more accurate than this guy, okay? And so you can actually use this scheme, as well. So all you have to do is basically follow the exact same process and apply this equation here at different values of I, and that will give you different coefficients in this matrix right here, okay? The only caveat with this is that because we have phi I minus 2 and phi I plus 2, if you want to use this equation here, you obviously need to have two neighbors. You need to have two neighbors on the left and two neighbors on the right, okay? And so you can actually only apply this, for, nodes starting at I is equal to 3, right? Because if you apply it for other ones, you know, you try to apply it for this guy, you're going to run into nodes that aren't on your mesh. Okay. And so, you know, when you're using these higher order schemes like this, you have to be a little bit careful on which nodes that you apply it on. Okay. And so you basically want to make sure that you have enough neighbors in order to accomplish all of these terms. Okay. And then the way that you actually write the loop for that is you can just write another if statement, right? And so you can make another condition here. And so let's say that we do else if row index is greater than 2 and row index is less than n minus 1. Okay. And so from here, this basically guarantees that, you know, we're in these middle entries right here, you know, where we have enough neighbors in order to actually compute this scheme. Okay. Okay. So we'll do more with this later on in the class when we get into higher order convection terms. But I just want to kind of introduce the idea right now, just so that, you know, just to tell you that this scheme right here isn't the only one out there. This is the one that we'll use 90% of the time, but you can fill in other schemes out there as well. So actually, you can actually look up on Google and Wikipedia for other finite difference schemes for, you know, and you can find out all different kinds out there. So there's as many finite difference schemes out there as, you know, probably pennies in your pocket. Okay, so it's there's a lot out there. Yeah, and actually there's a lot of research out there. So a lot of the research in these kinds of methods right now is determining, you know, what are the best numerical schemes for certain kinds of problems, right? And so, you know, kind of just taking a step back, you know, right now we're applying these to basically heat transfer problems. But, you know, there's different schemes that might work better for like fluids type problems, or maybe different schemes that work better for like structural problems, right? And so there's a lot of research out there that goes into saying, you know, what are the best schemes that we can use for heat transfer? What are the best schemes that we can use for structures, right? And so, you know, these are kind of the most basic of the basic here, but, you know, they get a lot more complex from here. Okay. All right. Yeah. And it gets even more complicated like that too, like Monte Carlo methods and integrals and all that really fun stuff. Yeah. Okay. Any questions on this? And so, you know, I mentioned that because I just want to make you guys aware that that different schemes are out there. But for now, you know, we're just going to use just the most basic schemes, because we're still kind of just learning, you know, how do we actually implement these in MATLAB, and how do we, you know, actually solve problems with these. So, you know, we won't have to worry about this until much later in the class, but I figured now is kind of a good time to mention this, just so that, you know, when we come back to it later on, it's not a completely foreign concept. Okay. Okay. All right, and so the last thing I want to talk about here is errors, okay? And so if you remember, you know, the error in a solution like this is defined as, you know, the difference between what we compute and what the exact solution is, right? And so actually, let me go back here and we turn this back to 50, okay? And let's look at our graph here of our finite difference solution with n is equal to 50, okay? And so you can see here, you know, the graphs here are pretty close, but there's still a little bit of a difference here, you know, near the tail end of our graph, okay? And so the reason for that is because we have errors, okay? And so the way that we define errors is as simple as this. So we basically just take the difference in between our finite difference value, which is our blue curve, minus our exact value, which is our red curve, okay? And of course, this is only valid when we have when we have the exact solution, which, you know, sometimes isn't always available, okay? And so let's actually modify this code right here so that we actually compute the errors, okay? Let me minimize this. And so let's actually compute the errors in our finite difference solution, okay? Okay. And so the way that we can compute the errors is we can just basically apply this exact formula right here, right? And so let's call this FD error, okay? And let's have this be the difference between FD solution, because remember, FD solution here, that was our approximate solution that we computed up here, okay? And then let's just simply subtract the exact solution, okay? And so this will basically tell us on a node by node basis how far off our finite difference solution is. And so this will tell us on a node by node basis how far off our FD solution is. Okay. Okay. And so we can run this code. I have an error. Oh, I did the exact same error as someone from earlier, so I didn't make that capital. Okay. Okay. And so now let's look at the errors here. Oh, whoa. Why is it like that? FD solution. Solution exact. Ah, sorry. And so the reason I got a matrix here is because, you know, our FD solution for some reason is a 50 by 1 vector, and then our exact solution is a 1 by 50 vector. So these dimensions have to match. And so what I'm going to do is I'm simply just going to transpose one of these guys. And so the MATLAB shorthand for transpose is just the apostrophe sign. Okay. So I'm going to do that. Okay. And you can see now that we have a vector here for all of the errors. Okay. And so you can see our errors are 0 at the left-hand side of the domain, and then they reach a maximum value of 0.0608 on the right-hand side. Okay. Okay. And so this is fine. And so this is a fine error, a fine measure of the solution. But just like, you know, just like we did with the solution, we might as well plot this guy just so that we can actually see or better visualize how big the errors are. Okay. X label, we'll call this X, and then Y label, we'll call this Y, or error. Okay. Okay. And so let's go ahead and plot this guy. I run the code. Okay. And you should see our error kind of linearly increases here. So it starts at 0 on the left-hand side of the domain, and then it reaches a maximum on the right-hand side. Okay. And so if you compare this to our solution plot, right, and you can see it should kind of correlate with this guy. So we can see we have an error of 0 here, and you can see on the left-hand side here, our solutions kind of exactly match up. So they're perfectly matched. But as we get kind of further and further in domain, our error goes up, right? And that's reflected in our error graph. Okay. Okay. And so, you know, what does this kind of tell us about our solution? And in particular, you know, what does this tell us about, you know, the accuracy of our different boundary conditions? Okay. Okay. Because if you remember from our problem setup, we set a Dirichlet boundary condition on the left-hand side of the domain, right? And so we basically force the solution to be 1 on that left-hand side, okay? And so since this is true for both the finite difference solution and for the exact solution, it makes sense that our error is 0 on the left-hand side, right? Because if we're forcing both things, if we're forcing, you know, both the approximate solution and the exact one to have the exact same value, it makes sense that their error is actually 0 there. Right? And so if you look at this graph, you can see, you know, that's the reason they both start at the same point right here, is because we're forcing them to have the same value, right? And so this result here is generalized. So whenever you have a Dirichlet boundary condition, you can generally expect the errors to be, you know, really low there, because we're forcing the solution to have a certain value, you know, and then if we force that same solution value on our exact solution, then it makes sense for their errors to be 0. Okay. All right. Whereas on the other side of the domain, we have a Neumann boundary condition, right? And so if you remember, for a Neumann boundary condition is a constraint on the derivative of the solution, okay? And so a constraint on the derivative is a lot weaker of a constraint than on the solution itself, okay? And so as you can see here, as we get closer to the Neumann boundary condition, the differences in between the two solutions are bigger, okay? And so, you know, in reality, once we get over here, the solution is kind of free to do whatever it wants. The only thing that's constrained is the derivative, okay? And so if you check the slope of the lines here, it's a little bit hard to see from here, but the slope of the lines at the ends of the graph are the same, which is, you know, what our Neumann condition specifies, but the actual solution values are different, okay? And so generally what you can say is that, you know, whenever you have a Neumann boundary, that's where your errors tend to be the highest. Okay, because at the Neumann boundary, we're not forcing the solution to take any certain value. We're forcing the derivative of the solution. Okay, and so whenever you do that, you tend to have kind of higher errors in those areas. Okay. Okay. Any questions on that? Oh, other graph. Yep. Oops. Yep. Mm-hmm. Okay. All right. Oh, question. All right. So the question. So there are a couple of questions. So one, will the number of points we have on the graph affect the error? Absolutely. Right. So remember when we talked about convergence, generally what you expect is that as you make the grid spacing smaller, our errors are going to go down, right? Because remember, that's what we found in our Taylor series approximation. And so if we increase the amount of grid points, then that's going to decrease the grid spacing, right? And so let's go ahead and increase the number of grid points to 100 here. Okay. And so you can see here that when we increase the grid points to 100, the kind of the difference in between these two graphs is getting smaller, and our error here is much lower at 0.03. Yeah. Right. And so the question is, so at the end we have a 6% error. It's not that the error is 6%. It's that the absolute difference in between the solution values is that. And so in this case, I think since the exact solution reaches a value of -1 at the end, I think it ends up being like a 6% error. But you can see, but the error that we actually compute here is actually an absolute error. So it's not a relative error. Yeah. And so you can compute relative errors if you divide it by kind of the original value. Right? So we can actually do that too. So actually, once we do this, let's do dot divide by solution exact. Okay. And so by dividing by solution exact, this will give us a relative error, right? So that'll be a percent error. Whoa. Okay. In theory, that's I need to do that. Okay. Yeah. Yeah. So it's I think I need to look at it because I think because we have some errors here that are 0. I think it kind of messes it up a little bit. And because our solution changes sign, but that's kind of the idea in order to get relative errors, that you have to divide kind of by the original one. Yeah. And so that original 0.06 that we found, that was kind of an absolute error, not a relative one. Mm-hmm. Okay. And so one last thing I want to mention here is that these graphs of errors are nice, but sometimes we just want a single number, right? Just to tell us how far off we are. Okay. And so one way that we can do that, or let me actually delete this code right here, is we can compute an aggregate error. Okay. Okay. And so we can do this one in a couple ways. Okay. And so one way that we can do this is we can just simply add up all the errors. Okay. And so we can say that total error is equal to sum of FD error. Okay. And so, the MATLAB function sum is a useful one because it'll take a vector and add up all the entries in that vector. Okay. Oh, one thing we need to do is we need to add up the absolute value of these errors. Okay. And so I've used another kind of MATLAB special function here called abs. Okay. Nothing to do with abdominals, but it's abs for absolute. And so what that'll do is that'll compute the absolute value of every value in that vector. Okay. And so after we compute the absolute value, we can just then sum it up. Okay. And then we go to our console here, and we can see here we have a total error of 1.51. Okay. And so you can think of that as all of the errors kind of added up in your entire solution. Okay. Okay. But this right here isn't that useful because, sometimes, you don't want, because the total, just adding up all the errors itself just isn't, it's a little bit hard to interpret that. And so another better metric might be the average error. Okay, and so for the average error, all we're going to do is we're going to take the total error and just divide it by the number of grid points. Okay, right. And so you can see here now we have an average error of 0.0151, and so that basically tells us that on average. On average, you know, the difference in between our exact solution and our approximate solution is 0.0153. It's kind of like DoorDash, but it's my fiance, so she's getting ready to cook dinner. It's like DoorDash but better. Yeah, so they should be different. So the total error and average errors. Oh, you mean they're different from this? Try changing your number of grid points to 100. Yeah. So your average error is going to depend on your number of grid points. Yeah. Yeah. Mm-hmm. Yeah. So absolute error in this case, that's basically the difference in between your approximate solution and your exact solution, just absolute value. And so when you take the absolute value, then you just, that's basically just to make sure that if the kind of the sign changes in between those, we're not kind of canceling out those numbers, because we want a sense of how far off in total we are from our solution. Yeah. So that's why I take the absolute value there. Okay. All right. Any final questions on any of this? Okay. All right. So total error. So what total error is telling us about the system is that our finite difference solution is has adding up all the errors at all the nodes. That gives us our total error. But again, the total error is usually not that helpful because that's going to depend on the number of nodes in your system. It's just kind of a little bit hard to interpret, because I think what's a better way to interpret the error is to take the error at each node and then just average them out for the entire system. And so that basically tells you that on average per node, our solution is off by this much. Yeah. And so total error, again, is not that useful because it's hard to interpret, but the average error is usually much more useful. But in order to get average error, we need to compute total error first. Yeah. Okay. Does that kind of clear things up a little bit on those metrics? Okay. All right, so we're out of time for today. So thank you guys for tuning in. Hopefully that this MATLAB activity was useful and help get you guys going for the homeworks. Okay. And so remember the check out. Go ahead and start homework 2, because it's a bit of a lengthy one, although we kind of did a big part of it here. Right. And remember, we have no lecture on Monday because Monday is a holiday. So the next time I see you guys will be next Wednesday, right? So have a good long weekend. Stay safe out there. Have a good evening, and I'll see you next week.
Thank you, Professor.
Thanks, guys. Oh yeah. Yeah, you can still post things on Discord as well.
Oh, here?
It's
Thank you.
all right, Daniel. Did you have any more questions? Okay. If not, I'm going to end the call, and I'll see you next week.